Ladies and gentlemen, thank you for having me today here. My name is Robert Arlinghaus. I'm a professor of Indian fisheries or fisheries management at the Humboldt University of Berlin. I'm also working as a senior scientist at the Leibniz Institute of Freshwater Ecology and Indian Fisheries in Berlin. And today I'm presenting a paper that is jointly authored with Rob Ahrens and Michael Allen from the University of Florida and Carl Walters from UBC, where we are going to present a paper, a model, where we systematically studied whether saving large fish through harvest lots may outperform the classical minimum length limit, and when it is judged against several fisheries objectives. So not only maximum sustainable yield, but also other objectives. The background of this work is that you have the classical textbook example of how fish stocks respond to exploitation. So if you start to exploit an unexploited stock, you will increase the yield initially because the fish stock responds by density-dependent compensation. And at some point, you will reach the maximum sustainable yield. And if you fish harder, you will enter a zone of growth overfishing where you don't let the fish grow for long enough. So the biomass that can be accumulated is no longer maximum. And at some point, you will also get recruitment overfishing, which is the red zone. But from this simple figure, you can also see that there are substantial opportunities for trade-offs here. If you are a commercial fishing industry, for example, you're very likely to benefit most if you manage the stock at MSY. However, if you're an angler, perhaps you're not even interested in removal of fish, and you might be interested in maximizing catch rate, which you achieve at an unexploited stock where the abundance is maximum. And similarly, a characteristic change of exploitation is usually that the fish no longer get old enough, and therefore the average size of the fish declines if you start exploiting the stock. So if also the catch of large fish is of value, for example, for recreational anglers, but also for conservation, you want to fish at levels that are below those that maximum sustainable yield would demand. So here are the trade-offs, and our study actually will investigate the classical way of managing fisheries, which is using some minimum retention size or minimum length limit, and compare that to situations where you also let the big ones go. But historically, the justification for minimum length limit was that you let the fish grow until they reach some optimum length or optimum size. Usually it's the age class where the biomass peak is achieved, and that is in the classical yield per recruit model of Bevan and Holt, the optimum length that you should basically manage for. And this is a classical justification out of the 50s, literature in the 50s and 60s that has called upon this management reference point. In addition, there are arguments that having a minimum length limit is important to let the fish spawn at least once. So this principle is also very well developed and well known to everybody, including many, many stakeholders. And if you do that, the assumption is that the fecundity of a fish stock is large enough and enough spawners will survive so that reproduction no longer is a key issue to be concerned about of those processes that govern the stock dynamics, which are growth, reproduction, natural mortality M, and fishing mortality F. So that's the 50s, the 60s, and arguments that prevail until today. There is, however, a recent or more recent literature, let's say 15 years old, where more and more people are claiming that actually minimum length limits downweigh the importance of large body size. And in effect, large individuals are of no ecological importance in such perspective, as long as enough spawners survive. So there is this emerging conservation debate that says, by the way, larger fish are not only more fecund, but actually they might also have better egg quality. There are many other reasons why resiliency of a fish stock should be larger. If also large fish are present, for example, that you have leaders in fish schools, experienced individuals, and not the least, for some fisheries types, particularly for recreational anglers, large fish on the hook usually generate more utility than a smaller fish. So there's also a fisheries argument that in certain cases, a large fish and their conservation might be really important. Recent research has further argued that neglecting the ecological importance of large fish might be a problem. So here, a paper recently from Science by Bernesh et al. That actually re-examined a classical assumption that many stock assessment models have, that is that the fecundity scales linearly with the mass of the fish. So note that this is logarithmic scale, and the exponent here on average was 1.18. So in effect, they showed that in a big meta-analysis that the fecundity is non-linearly related to the mass. And at a hypoallometric scaling of 1.33, for example, here in cod, you will see very, very different predictions of an individual fish and his fecundity, comparing the isometric one-on-one relationship basically to the one that is more supported by recent data. However, just counting eggs doesn't mean that big fish matter for population dynamics, because you have to account for density-dependent population regulation, for size-dependent mortality, and many other things that determine whether an individual egg actually ultimately results in a recruit that is being entering the fishing. So we need to develop population dynamic models to actually test whether this hyperallometry in fecundity is actually of importance at all, and whether it changes the classical predictions what is an optimal regulation. And that is what our paper is about. We studied and constructed models and systematically examined whether minimum length limits or harvest lots were considered the optimal regulation under different assumptions about population demography and population regulation processes. The first question we ask is, which regulation achieves the optimal outcome for a single fisheries objective? Either you want to maximize biomass yield or numbers yield or catch rate or the catch of large fish. Second question is, which regulation achieves the best compromise if you have more than one fisheries objective? So you can now combine any of those four or all four together and ask which regulation does the best job in meeting multiple objectives jointly. And then we examined how robust the optimal regulations that the model spits out is to variation in key processes that govern fish stocks. Particularly, we changed the stock recruitment relationship, the degree of density dependence in growth, and the degree of size dependence in mortality, among other things. Particularly, we also asked, how do size-dependent maternal effects affect these outcomes? So maternal effects are effects of the phenotype of the female, in this case, on the phenotype of the offspring. And there are actually two variants of maternal effects. One is larger fish can have a higher relative fecundity. That's the hyperallometry argument. And the second is that there might also be better egg quality. So higher survival probability of eggs spawned by larger fish compared to smaller, which is a controversial topic, how relevant this effect is in population dynamics. So we systematically explored the sphere of possibilities, so to speak, to see whether it matters or not in a model. So we used classical age-structured fisheries model, and Rob Ahrens is shown here, who is the master brain behind the model development. Also, Carl Walters did a great job here initially. So we used the classical age-structured population demography, but we allowed several relaxed assumptions compared to the classical yield per recruit model. For example, we included density-dependent growth. We simulated two different stock recruitment functions, Bevan and Holt and Ricker, and we have size-dependent fecundity of different degree and size-dependent egg quality of different degree that we vary systematically in the model. And the model spits out given outputs, such as the biomass yield, the numbers yield, the catch rate, and the catch of trophy fish for a given fishing mortality rate. And we then ask, we do an optimization of the whole model to ask, how would you change the size selectivity to achieve either a maximum single objective or a maximum combination? And of course, anything that you change in a time step will affect next year's processes through changing the size structure and changing the density dependence. So this is a little sketch of the key processes that we try to model. So first of all, we distinguish between Bevan and Holt and Ricker type stock recruitment. So the Ricker type is more characteristics of cannibalistic species, Bevan and Holt more of non-piscivorous fish. We included density-dependent growth. So here the Fombetta-Lamphy size at age predictions vary strongly, whether you have a large density or small density. And we also had several assumptions about size-dependent mortality. So the classical yield per recruit model has a constant natural mortality rate, and we make it more biologically plausible that the younger fish have much higher mortality than the older fish. And then we simulated the fecundity relationships either with hyperholometry. So here you have the exponential increase in fecundity with length as one scenario. And we also had assumptions about the egg quality that could vary by spawner. And all of these things affected, for example, the resiliency of harvest and the type of yield that you can get if you vary, for example, here on the bottom right, variations in density-dependent growth and size-dependent mortality. It will also affect the spawning potential ratio. And if you vary the egg quality, you will change the slope of the stock recruitment curve. And we systematically ask, how does this alter which regulation is predicted to be optimal? And here is one and the first key result. Here is a single objective. We want to maximize the biomass yield for the entire range of density-dependent growth. So if that parameter is 1, there's no density-dependent growth, and it increases if you move up here the x-axis. And if you move up here the z-axis, you have an increasing degree of size-dependent mortality, from no size-dependent mortality to very pronounced size-dependent mortality. And on the y-axis, you have L over L infinity. That is basically the size limit that is predicted to be optimal. If you see only one plane here, it means in all cases, a minimum length limit is the optimal regulation. No matter what the degree of size-dependent mortality, what the degree of density-dependent growth is, and independent of the stock recruitment function, in all cases, a minimum length limit is predicted to be optimum for maximizing the biomass yield. And as the stock becomes stronger regulated by density-dependent growth and size dependency becomes more pronounced, you can fish harder. The fish enter already earlier into the fishery. So that means the fish stock is more resilient to the harvest because it has this compensatory potential to deal with the removal of biomass. So at that level, the textbook is confirmed. People have said this for many years. If you're only interested in biomass yield, a minimum length limit is a good idea. And we confirm this for a wide range of processes that is out there. However, if you are, for example, an angler, you might not be interested in biomass yield, but in numbers yield. Imagine you are a small little angler community, you exploit a series of 4, 5, 6 lakes. It's probably better for the whole community if the numbers of fish that are reasonably large to be harvested is maximum, because then you can distribute them more equally among people. And if you change that little bit from a biomass yield to numbers yield, you see here that an upper plane emerges. And in all cases, actually, a harvest slot becomes the optimal regulation. And again, as the fish stock enters density dependence in growth and size dependent mortality, the fish stock is more able to withstand the harvesting pressure, and therefore more liberal harvest slot is predicted to be optimal. If you now change to a single objective of optimizing the catch and therefore the conservation of big trophy fish, you find a very interesting picture that at stocks where there's limited degree of density-dependent growth, actually zero exploitation is predicted. The upper and the lower limit are actually on top of each other. But in stocks where you have density-dependent growth to be very prominent, actually, again, a harvest slot is predicted because you need a little bit of harvest to remove the density-dependent control and actually foster particularly fast growth rate. And again, a harvest slot then becomes the optimum regulation for the single objective. The reality will be that a manager usually wants to achieve multiple objectives jointly. And if you add just one additional objective to biomass yield, for example, numbers yield or catch of trophy fish, in all cases that we modeled, we get the result that a harvest slot is the optimum regulation. No matter what you do, in all cases, if you have biomass yield plus something else, the best compromise is predicted to be a harvest. which objectives, how good are you meeting those multiple objectives at that optimal regulation? That is shown here for the entire range of simulations that we did. And you see that for all the 4 objectives, more than 50% of the maximum is achieved. The biomass yield is actually the lowest of those 4 objectives, no matter whether you have Bevan and Holt or Ricker type recruitment. So you do pretty good on all dimensions, but you cannot achieve 100%, obviously, because you are maximizing 4 objectives jointly. By the way, we did this with a logarithmic utility function. So there's no way that a single objective can be compensating for another one. You have to do well on all 4 to some degree. So what does this mean on this classical yield curve that I started my presentation with? Well, basically it means that the optimal regulation when you have multiple objectives means that the fishing mortality is smaller than the one that maximizes maximum sustainable yield. And I would argue that, and we would argue that this is often the case in recreational fisheries, that you are better off at not harvesting the stock as aggressively as you would do it, perhaps, in a commercial situation. Finally, what are the results or systematic impacts of adding hyperallometry and fecundity? Here a different version of our results, where you have on the x-axis the fishing pressure as expressed as F over M. And you see that if the fishing pressure increases, here the black line is the optimum minimum length. 4 simulation runs where you have isometric relationships between mass and fecundity, so a linear relationship. Minimum length limits are predicted to be optimal. What happens if you have hyperallometry and fecundity? Well, first, nothing happens, but if the hyperallometry becomes strong, over 1.2, for example, suddenly upper maximum length limit starts to be put in. So while with isometry, it's even for biomass yield optimal to have a minimum length limit, it changes when hyperallometry and fecundity is large. Then, even for the biomass yield, a harvest slot is the best solution. However, the fecundity change with math has to be very strong, and it is an empirical question how strong it is for a given stock. So here, empirical biologists have to come up with data to support whether that maximum, exponent of 1.2 or 1.3 or something like that is actually achieved. So if we summarize, a manager usually has to deal with multiple objectives jointly. And you can, have fisheries objective, you can have conservation objectives, and if the fisheries objective is to maximize biomass yield, for a large range of cases, we would argue a minimum length limit is the best solution. However, if you are interested in maximizing the numbers of fish that are taken, a harvest slot becomes optimum. And whenever you are dealing with a compromise, you have maximum biomass yield as an objective and something else like trophy catch, high catch rate, or the numbers of fish that are to be harvested, then a harvest slot becomes the better solution. From a conservation perspective, if the only objective is to avoid collapses, a minimum length limit could do the job, but also a harvest slot is not a bad idea. If you want to have a more natural age structure, I didn't have the time to go into that obvious finding in my presentation, but you have to believe me now that a harvest slot, if the fish are able to grow through, so the fishing mortality rate is not too high, it creates a more natural age structure in most cases. So you would go for that regulation. If you want to have an increased resiliency, particularly because you don't know all the other mechanisms by which large fish contribute to population renewal, to migration, experience, etc., we would argue a harvest slot is probably a better bet. And if you want to achieve a higher standing biomass, again, if the fish are able to grow through a harvest slot, promises to be an optimal regulation. What we also found is that hyperallometry and fecundity even changes the biomass yield prediction. And for time reasons, I didn't go into detail. We didn't find lots of evidence that maternal effects on egg quality is actually of relevance in arguing which regulation is optimum or not. So it didn't affect our results to a large degree, and therefore we think they are pretty irrelevant for the optimum regulation choice. If you want to read through the details, this article is published in the journal Fish and Fisheries, which is an open access article, and of course you're happy to to read it out. And with that, I want to thank the lab, but particularly the 3 big modelers, population dynamic people behind this research, Rob Ahrens, who did the model, also Carl Walters, who actually helped a lot in the initial phases of the project, and Mike Allen, where I spent a little bit of a sabbatical a few years back, and where the idea for this paper actually was born. And with that, I want to thank you for your attention, and I hope that we engage in an interesting discussion through the chat or whatever option AFS has. Thank you very much.